Hi, my name is Lauren Biernacki, and I'm a fourth-year PhD candidate at the University of Michigan. I work with Professor Todd Austin, and today I'll be talking about our ongoing work exploring the question, can hardware enclaves be as powerful as homomorphic encryption? With the increased dependence on cloud computing services, data privacy has become a significant societal concern. Critical applications take advantage of vast computing resources in the cloud to process and store personal data. However, the confidentiality of this data is not guaranteed. Consider the following motivating example. A user wants to take advantage of a new cloud service to learn of her genetic destiny. However, she's hesitant to just upload her genetic information to the cloud. Ultimately, the human genome is not like a password. You cannot change it if it's stolen. There's only a single version. If her genome is leaked, it's gone for good. In this system, there are multiple points of failure. An adversary may be observing the user's communication with the server. Or perhaps an adversary was able to exploit a bug and hack into the server's software. Worse, the administrator of the server may be corrupt, selling a user's genomic data to other companies. Traditional techniques for data privacy encrypt client data during transmission and while at rest on remote servers, protecting against only some of these points of failure. With these techniques in place, genomic data still exists as plain text within the system. Thus, privacy is only ensured if these plain text values are inaccessible, requiring the remote server to be impenetrable, software to be unhackable, and the administrator to be trustworthy. As evidenced by the continual security arms race, this cannot be confidently achieved. Luckily, two recent advances in privacy technology enable us to also protect data within the system itself. Two approaches reign supreme when it comes to protecting data during computation: secure enclaves and fully homomorphic encryption. But these runtime techniques are not absolute. Secure enclaves, like Intel SGX and ARM Trust Zone, provide a practical solution to data privacy. These technologies enforce the confidentiality and integrity of private data, using both system and hardware support. However, state-of-the-art enclaves have two major design flaws that leave them vulnerable to penetration. First, these enclaves include vulnerable software components. Having any portion of key exchange or encryption that occurs in software leaves sensitive values at risk. Second, enclaves share hardware resources with untrusted processes, without always protecting the data in these shared structures. Sensitive data and secret keys are stored in shared structures and are susceptible to side-channel attacks. The foreshadow attack illustrated both of these design flaws. Some Intel SGX policies are implemented in software due to their complex nature. These software components need access to secret key data, pulling these sensitive values into shared memory and leaving them vulnerable for extraction. The foreshadow attack was able to extract this key data from shared caches by exploiting timing side-channel attacks that are innate to modern memory systems. Fully homomorphic encryption, or FHE, provides a cryptographic alternative to secure enclaves. FHE preserves operations performed on ciphertext, making it ideal for outsourced, privacy-preserving computation, as operations can be performed without access to secret keys or plaintext values. For this reason, FHE has been touted as the holy grail of data privacy. But FHE also has major drawbacks. Although advancements in FHE are developing rapidly, the scheme's poor performance makes it impractical for use in the near future. Accelerating homomorphic encryption is an active area of research, but it's extremely tedious, often involving heavily optimized algorithms for very specific applications. Performance overheads are still too high to be practical for general use. Furthermore, FHE lacks programmability, and there are still open questions about the strength of such a new encryption scheme, as it is not time-tested like AES or RSA. Ultimately, both of these technologies are valuable, but fully homomorphic encryption is impractical given its current state, and the systems-based alternative is vulnerable. So we pose the question, can hardware enclaves be as powerful as homomorphic encryption? We argue that this is possible if microprocessor enclaves leverage sequestered encryption. Sequestered encryption is a novel technology that has the potential to push microprocessor enclaves forward to a point where they have the capabilities of FHE with the system design aspects of traditional enclaves. Sequestered encryption confines plaintext values and secret keys into a small hardware root of trust that is inaccessible to the software layer. This privacy approach is based off of two design axioms. There are no software components, and there is no microarchitectural sharing of sensitive plaintext or keys. These axioms fix the two big problems with existing state-of-the-art. It removes all software from the enclave, and it sequesters all decrypted data and secret keys into trusted storage, stopping the side channel attacks that have plagued Intel SGX. Furthermore, to be as or even more powerful as FHE, we can use sequestered encryption to design a system that is significantly faster, much more programmable, and is built atop time-tested crypto algorithms. What may be obvious here is that sequestered encryption requires trust in hardware. This perhaps is the one loss to FHE, as homomorphic encryption only requires trust in the mathematical foundations of the scheme. However, in our work, our hardware root of trust is a small subset of the pipeline logic, small enough to be formally verified. We regard this trade-off as adequate for a majority of applications. With sequestered encryption in these two design axioms, there's no more software hacking, and there's no more timing side channels. All that is left to infiltrate the system is to break the crypto. There is something super fundamental about the security claims here. By eliminating software and shared storage, really we get down to this basis of having to break the cryptographic scheme. We can fully mimic the security model of FHE while providing the system design benefits of secure enclaves. To implement sequestered encryption in a microprocessor enclave, we must adhere to both hardware and programming requirements. In hardware, we must sequester all sensitive plaintext and keys from the core. We enforce a strict partitioning between public and private values by using trusted hardware to operate on keys and sensitive plaintext. Additionally, these sensitive values are encrypted in all other shared structures. Since private data is encrypted in the untrusted core, we must ensure that these values remain secure. This warrants strong encryption schemes and large salt values to prevent adversaries from committing cryptanalysis attacks. Sequestered encryption also necessitates programming requirements. Specifically, software cannot examine sensitive plaintext, since these values are only revealed within the enclave. Thus, we must adopt data-oblivious programming. In the following slides, we'll go through these requirements in more detail to see how they are integrated in our microprocessor enclave design. Let's begin by looking closely at the hardware requirements. In a traditional enclave, public and private data are intermixed in memory and in the register file. Private values are not protected and exist as plaintext, leaving them vulnerable to exfiltration. In our enclave, we sequester all sensitive plaintext and key data from the core, enforcing a strict division between public and private data. Outside of the enclave, private data must still travel through memory, so we encrypt it. All private values are replaced with secure ciphertext. All microarchitectural structures in memory now contain encrypted data. No sensitive plaintexts are ever exposed in shared structures. Since ciphertexts exist in the main core, we consider them visible to attackers. It is very likely that an attacker will attempt to leak sensitive values by using these ciphertexts to break the crypto scheme. In response, we employ strong, time-tested encryption schemes with significant salt values to defend against cryptanalysis attacks. Specifically, to form a ciphertext, a plaintext value is extended by an 8-byte salt to adequately diversify the result, and then this extended value is encrypted with AES. To implement sequestered encryption, we must also impose trusted hardware for key exchange. We sequester all key-related data into hardware and augment our instruction interface to facilitate key exchange without exposing sensitive values to software. The server's private key is stored in a dedicated hardware register within the enclave. This register is inaccessible even to the most privileged process. The enclave's hardware key exchange protocol uses this hidden private key to receive a symmetric key from the client. Because this protocol is founded in hardware, we can perform key exchange in a single atomic operation, while never exposing the symmetric key or private key to software. Our dedicated hardware ensures that this protocol is secure and cannot be observed by the operating system or other processes co-located on the server. Finally, we must also include trusted hardware for plaintext computation. Within the enclave's trusted hardware, private data can be safely decrypted, enabling privacy-preserving computation. Trusted functional units within the enclave operate on sensitive data. And this computation is facilitated by a RISC-style instruction interface between the enclave and the core. Custom instructions in this interface, like encrypted add, direct the processor to enter the enclave during the execute stage of the pipeline. Within the enclave, the source registers are decrypted before the operation is performed. Afterwards, the result is re-encrypted and passed back to the core. Thus, plaintext values are only revealed within the enclave's functional units, which we assume are unobservable and part of the trusted computing base. No path between the functional unit and the register file or memory exists that does not pass through an encryption unit. Finally, the instruction interface enables a fine-grained interleaving of operations on public and private data, which serves to reduce the performance overheads for real-world applications. Given this hardware implementation, let's take a look at the programming requirements for using this secure enclave. While programming our microprocessor enclave, we adopt data-oblivious programming, as the core cannot examine plaintext values. Data-oblivious programming is a technique proposed by prior work to prevent confidential data from propagating to observable outlets. Specifically, sensitive values could not be used as memory addresses or as the condition for control flow statements. This code excerpt computes the Levenshtein distance of two inputs. This algorithm is often used in genomic applications to compare two genome sequences. This algorithm iteratively traverses a fixed size matrix in a set order, calculating each element sequentially. Because this traversal is not input dependent, the loop variables are not sensitive. We can use primitive unprotected data types here. Similarly, we do not need to protect constants, as this algorithm is well known. These public plaintexts are unprotected in shared structures and operated on in the main pipeline. They also do not need to adhere to data-oblivious programming. However, the genomic data and the content of the matrix is secret. These variables are protected and encrypted in all shared structures. All operations on these values are handled within the secure enclave, and these operations must adhere to data-oblivious programming. We can also make decisions on these secure ciphertexts by using a conditional move instruction that is handled within the enclave. In this algorithm, the conditional moves are used to find the minimum of 3 values. I don't think this would be as easy to compute using fully homomorphic encryption. Let's take a look at how these programming requirements interface with our enclave design. The program is compiled using instructions from the enclave's instruction interface, like encrypted add. When these instructions are executed, the core redirects control to the enclave and provides the instructions inputs. These inputs are decrypted, operated upon, and re-encrypted in one single atomic operation. And this final result is passed back to the core and stored in the destination register. Due to the nature of this implementation, we can limit what operations are permitted on sensitive values by restricting the instruction interface. we can use our instruction interface to enforce data-oblivious programming. Thus, we restrict the instruction interface to only include arithmetic operations and conditional moves, prohibiting decrypted data from being used as a jump target or as the effective address of a memory instruction. Even if these operations are prohibited in the enclave, they may occur in the pipeline due to a malicious process manipulating program execution. But these operations only have access to the ciphertext since they're computed in the main core, so they cannot leak private data. For simplicity, let's consider if this instruction was just a regular old addition. This operating code would not be redirected to the enclave. The execution of the main core would operate on the ciphertext, producing garbage and leaking no information about the underlying plaintext. Thus, even if attackers can manipulate execution, they cannot learn any information about the decrypted value. This brings us back to the two design axioms of sequestered encryption. Without software or microarchitectural sharing, traditional hacking techniques and timing side channels are no longer valid. All an adversary can try to do to leak information is trying to break the underlying encryption scheme. This is super fundamental to our security claims about the validity of sequestered encryption. Returning to our motivating example, the user can now confidently encrypt their data with a key that they exchanged with the server. With support from our secure microprocessor enclave, they can be reassured that neither the software or operating system on the server will never know the true value of their genomic data. In summary, existing techniques to protect private data during computation are essential, but have proven to be either non-durable or costly. In this work, we aim to push microprocessor enclaves forward to the point where they are competitive with even the most enticing fully homomorphic encryption schemes. To do this, we leverage sequestered encryption in hardware. With the support of this mechanism, we can maintain data confidentiality in all hardware structures and ensure that sensitive data is never observable to the operating system or another process. By eliminating software and microarchitectural sharing, the only remaining avenues to penetrate our enclave is for an attacker to break the cryptographic scheme. We have implemented our sequestered encryption enclave in simulation and built a programming framework and instruction interface to aid programmers in developing applications for our enclave. This programming framework was shown previously during our discussion of data-oblivious programming. Currently, we are working to employ traditional architecture techniques to reduce the performance overheads of this design without compromising our security axioms. I encourage you to keep an eye out for an upcoming publication on this work, which will include these performance results. Overall, sequestered encryption in hardware provides a comprehensive data privacy solution that preserves confidentiality and adequately balances performance, security, and trust. Thank you for watching this video, and I'm happy to take any questions.